I forgot to change the sizes. All right. So, part one. What was part one? Undamped, free undamped motion. All right, this is the first one. All right, let's take a look at this. It says spring at rest, attach a mass. Spring is stretched by some amount S, and so according to Hooke's law, we have the force is proportional to the stretch of the spring. K is sometimes called the spring constant. So you combine that with Newton's law, and the force is equal to the mass times acceleration. And we have to also think about the force as being the weight if you're in the standard measurement, the US standard. And then we can have the relationship between the forces as mg is equal to ks. And so we can come up with a differential equation by combining that. We have the spring being pulled by some distance and then released. And so there's this thing that they're calling the restoring force. And we have to assume that there's no damping, free motion, there's no other external force. Then we have Newton's law. Mass times the acceleration is equal to eventually equal to negative k times the position. So I think from here we're going to make this a nice simple differential equation that we've already seen. So we're going to I guess copying stuff. We got the mass times, let's say x double prime of t is equal to k times x of t. And then we have, let's just say x double prime plus kx equals 0. Now, we generally want this to look like your standard standard differential equation. So we generally want the first coefficient to be 1. So let's divide by m both sides. We got x double prime plus k over m, x is equal to 0. Now, we're assuming that k is positive. We're also assuming that m is positive. And so when you look at this in terms of a differential equation that you're going to solve, this is a second order differential equation with constant coefficients. We have our auxiliary equations, and then we'll turn out having the square root of k over m times I think, as roots. So in fact, if we follow through this process, we have the auxiliary equation to be, oh, I can't use m anymore. Something, r for roots. R squared plus k over m is equal to 0, so r is equal to, this becomes a negative on the other side, and then when you take the square root of it, you get plus or minus square root of k over m. And then because it's negative, you take the square root of -1. It's going to give you a pair of complex conjugates. And then we should already, hopefully, immediately know the solution is going to involve sines and cosines. So what's it? It's y1 is equal to cosine and then square root of k over m I. Oh, there's no I there. We're using t's for our variables. Whoops. And then y2 is equal to sine. Okay. So the square root of k over m kind of describes some sort of frequency, and so they have a symbol for frequency in general when they do stuff in physics. And what's that? You guys know? Something. Sometimes they call this omega. So we have our differential equation, x double prime plus, well, omega is equal to the square root of k over m, so this should be omega squared. Okay. So let's remember what we have here. We have m is the mass, k is the spring constant. So here we kind of have the immediate solutions. We can go through the process of solving for it again, but we can just get the solutions directly, and the solutions then will just be y is equal to some constant cosine omega t plus another constant sine omega t. And then those constants can be solved for if you have initial conditions. And usually they tell you what the initial conditions are when you pull the string before you let go, or whether or not you let go or you actually put some initial velocity to it. Okay? I think that's, yeah. So they give a simple harmonic motion, perpetual oscillating, that because there's no damping, you can't expect it to stop. So let's see if we could do an example. There's a couple of examples here. One's in pounds and one's in newtons. Any preferences? Newtons. Oh, that's small. All right, here's our example. We have a force of 400 newtons that stretches a spring 2 meters, and then the mass of 50 kilograms is attached at the end of the spring and is initially released from equilibrium position with an upward velocity of 10 meters per second. The other conventions that they have here is usually they have the positive value going down. So that's how we can work out some negative numbers here. So we essentially want x prime or x double prime plus omega squared x is equal to 0. And now we have to figure out what omega is, right? So what's omega again? So we need some k or m. So let's figure out what k is equal to. Based on this information, a force of 400 newtons is going to stretch the spring 2 meters. So Ks, so force according to Hooke's law is equal to some constant times the offspring or offset. And we're dealing with newtons, so we're dealing with newtons, meters, and what's newtons? So this is going to be some constant times 2 meters, and the stretching goes down positive 2 meters. So let's say K, our spring constant, is equal to 200. Right? And then what's the mass? Mass is 50 kilograms. Do we stay with kilograms? And so here's our K and M, right? And so that's going to give our omega. Omega is equal to the square root of K. Is it M over K? K over M? K over M. So that's square root of 200 minus 50 divided by 50. 4, 2. Is that right? So that's going to be 4. We put it in here. So our differential equation is going to be x double prime plus 4x is equal to 0, which we've solved before. We know the solution to that already, but to help us actually find the arbitrary constants, we need to figure out what happens as with our initial conditions. So the position where this is released from, initial position, starts where? So it's released from the equilibrium, right? So I think the initial position will be 0. And then they give this an upward velocity of 10 meters per second. So your x prime will be 10. Should it be 10? Yeah, so the upward position, the upward direction is negative, the downward direction is positive. So I think we're all set. We have our initial conditions, we have our differential equation, so we have an IVP. And now we know the solutions. I mean, we could, if you want to have fun with it, find the solutions. But we know the solutions already. So y is equal to C1 cosine 2t plus C2 sine 2t. And we need to do derivatives to help us solve for C1 and C2. So the derivative of sine of cosine is negative sine, so there's a 2 extra that we want to put in. The derivative of sine is positive cosine. And then we want to put these values in. So we have x of 0 is equal to 0, so we're going to put 0 in. I guess this should be x. So when we put 0 in, the cosine of 0 is 1, sine of 0 is 0, and this is equal to 0. And then the derivative will have a 0 plus 2c2 times 1 equals negative 10. So it looks like here C1 is equal to 0 and C2 is equal to negative 5. And then, so we get our solution. So x of t is equal to 0 minus 5 sine 2t. Now the graph should be simple enough to be able to manage. We need to draw the sine function, and the sine starts off at 0, and then it has a period of it's squeezed a little bit, and it starts at negative 5. It starts going down first. Yeah. Just look at this upside down. So this is going up if you go this way. Well, that's what they do in physics, don't they? I don't know. So they want the gravity to remain positive, and so that goes down. Anyways, this is what we have. Any questions? So a lot of these things are going to rely on your solutions having combinations of sines and cosines. So there are going to be some times where they might want you to combine, since they're generally going to have the same frequency. They might want you to combine the sine and the cosine together. You guys know the trig properties for that? Kind of depends on whether you want to combine it into one sine or one cosine. Let's see. I don't know if I have that in my notes. Something like that. Let's backtrack a little bit and do some trig stuff. So sometimes you might have, I don't know if they use A's and B's and stuff. You might have a solution that you might want to combine. Into one trig function, and You can combine this into one sine or one cosine function. And I think in either case, your amplitude is going to, because when you add these things, it'll just be just another, sinusoidal function. So you can write this as a sine or a cosine. I don't know the formulas off the top of my head. I suppose we can look it up. We can find it, yeah. Phasors. Yeah, there's a phase shift, and we just have to figure out what that shift is. Just so you can have it in as a function of just one trig function. So we'll call this sigma sub s for the sine, and then or that's a phi, I guess. So we just have to figure out what these things are. And these things end up being like inverse tangent or something. Let's say arctan. In any case, the first problem that we did only ended up with one sine anyways, and the cosine disappeared, so it wouldn't be that big of a deal. But for future cases, it might be a good idea to know this formula, at least be able to look it up real quick. All right, let's move on here. We got our first example done with a simple harmonic motion that has no damping or anything like that, or external force. So let's try to do our next type of example, and our next type of example is an example that has damping. So in this case, we're going to have something that would not let your spring go on forever. It's damped by something, the air, gravity, or what's that? Some sort of friction thing. Sometimes they show these things with a beaker of water underneath to say that you're slowing things down. So with some damping force, the damping is related to the velocity. It kind of slows down the velocity. And so it's going to include your differential equation now. Initially had a second derivative and a position according to Hooke's law and Newton's law. But now we're going to throw in a term with the first derivative. So the damping force is proportional to the instantaneous velocity, so that's dx dt or x prime. And so assuming that, again, there's no other external force that's moving things around, then we have our differential equation begins to get set up like this. We have our mass times acceleration is equal to negative k times x, the position, and then we tack on another negative beta, some value times the first derivative. And so to again make it look nice, they have a more standard form of the differential equation where they kept the omega squared, the square root of k over m, um, as omega, and then they introduced this new variable called lambda. So you can probably figure out what lambda is, right? I mean, if we take a look at where this is coming from, we bring everything over to the other side so that it's equal to 0, and then we divide by m. So we have x double prime and then plus beta over m x prime plus k over m x is equal to 0. So the k over m is that omega squared, and then so the 2 lambda over here gets equated to this constant, the damping constant. So we got 2 lambda is equal to beta over m. Okay, and then this is still just another second order differential equation with constant coefficients, so we still solve it the same way we've been solving for it. We would make it into an auxiliary equation, use a quadratic formula to solve for whatever we need to solve for, and then we have our solutions. Now, the interesting thing about this is that they also have a set of parameters now that we have lambda and omega. If you do the quadratic formula on this equation, or on the resulting auxiliary equation, what is it? R squared plus 2 lambda r plus omega squared is equal to 0. We have our, what is it? R is equal to minus 2 lambda plus or minus the square root of 2 lambda squared. Let's put 2 lambda in parentheses. So that's b squared minus 4. A is 1, c is omega squared, all over 2a. And remember, the discriminant in your quadratic equation, quadratic formula, is what really matters and what decides what happens in your set of equations, whether it's going to give you 2 real roots, 1 real root, or complex conjugates. So if you look at this thing in here, that's essentially 4 lambda squared minus 4 omega squared. And you can take the 4's out, then you're just left with lambda squared and omega squared. So the 3 cases that we have there are when lambda squared and omega squared are both bigger than 0. That means the thing that's inside of the square root is bigger than 0. What do we have if the thing inside of the square root is bigger than 0? We have 2 distinct real roots. And so with 2 distinct real roots, we have our solutions to just be the linear combination of e to each of those roots times the variable t. If it's equal to 0, then that means we only have 1 real root, but that's a repeated real root. And so when we have a repeated real root, we have e to that root, and then we have t times e to that root, or that root times t. So here's our second solution. And our third solution, if it's less than 0, that means there's a negative sign that comes out, and that negative sign will be, we'll make it complex conjugates. And so you would have the combination of sine and cosine. Okay. So they have special names for that. For each of these, it's overdamped. And if we take certain values for lambda and omega, then overdamped just means it's gonna squish down really quickly. That means there's too much damping. There's not much spring action going on. Critically damp means it might go one up and then down, and then it'll dampen according to the exponential function. And then if it's underdamped, then it's gonna wiggle. So it's kind of like that picture that we saw. Where's the picture that we saw? Something like this would be an underdamped example. Okay, let's pick an example now. We have choice between pounds and kilograms again. Should we do kilograms again? Always? I'm already a character. What are we doing? Think we should do what? What do you guys think? It's good to know how to do both. I don't know. One's in kilograms, one's in pounds. So the thing about the kilograms is that the weight itself, when they talk about pounds, it's measured as a force. And so when you're looking for the mass, you have to divide out the 32 feet per second. You probably heard about it if you've done any physics with this stuff. Yeah. So if you've done physics in the math class, you probably know about slugs. Or we could just stay with kilograms, but what? Oh, I don't know. In the exam, I could put all the questions in kilograms and metric system. All right. So what if I don't give you any pound problems in the on the test, but there might be some in the homework already, so I'll let you figure that out. All right, let's do this problem. We have a 1 kilogram mass attached to a spring whose constant is so they give us the constant, the spring constant already, so that's the K. And the entire system is then submerged in a liquid that imparts a damping force numerically equal to 10 times instantaneous velocity. So they also gave us the beta. Yeah, so they gave us the beta. Determine the equation of motion if, so there's two parts to this. Let's just do one of them. Let's do A. So it looks like we have some information here. We have a 1 kilogram mass, so that's our M. M is equal to 1. We have our spring constant already given to us as a spring constant, so that's 16. And then we have a damping force numerically equal to 10 times the instantaneous velocity. So the damping force is given by beta. And if you remember that equation, the differential equation from the previous page, we're looking at the mass times x double prime. I think it was negative on the other side, so we bring it back on the other side, it'll be positive 10x prime plus 16x equal to 0. Oh, I should call this beta, and omega squared. Omega squared? I think it was just k. I haven't done the m yet. Let's just leave it like this. Let's just leave it like it's supposed to be k. You guys have a sheet of notes. You don't need to memorize anything. This test is going to be so easy. You guys get a sheet of notes. So we'll put in all our values. And then we can immediately jump to the cases that we have where we can solve for omega and lambda. But let's just might as well just go through this whole, what's it called, quadratic formula. So the question is 10 squared bigger than 4 times 16? What's 4 times 16? 64. 100 minus 64? 36. Square root of 36? 6. So we got minus 10 plus or minus 6 over 2. So we have two solutions, two distinct real solutions. So r is going to equal to, what's the first one? Negative 4 over 2 and negative 16 over 2. What? Oh, yeah, so I added it first. So negative 10 plus 6 is negative 4, and then negative 4 divided by 2. So I got these two. Does that look right? All right. So now that we have that, we can get our solutions. We have two distinct roots. Our solutions are going to be e to this power, e to that power with the constants. Y, or I guess these are x's, x of t, x is equal to c1 e to the negative 2t plus c2 e to the negative 8t. Yeah. Oh, yes, I guess we should. Well, I mean, we can ask ourselves at this point, or maybe at this point right here, whether this is critically damped or not. So is this, out of the three choices, is critically, no, it's overdamped. Yeah, so it's overdamped if you have two distinct solutions, and we'll take a look at the graph of that. And if it's critically damped, means it's damped just enough to have it go at least one time down below the equilibrium. And then underdamped means it's not damped enough and it wiggles, but it still gets enveloped, gets enclosed by the exponential function on the outside. All right. So we have our solution already. We didn't set up our initial conditions. Probably should have done that in the beginning, but let's do it now. So mass is initially released from rest 1 point at a point 1 meter below the equilibrium. So again, we're talking about the spring, the mass, equilibrium, positive, negative. So 1 meter below the equilibrium. So what's the initial position? Positive or negative one? Positive. So it's below. So I think it's +1, and it's quote released, which means the initial velocity is. So it's released from rest. So it should be 0. We're not pushing it or doing anything weird like that. It's like those ball problems back in Calc 2. When you have a ball up in the building and you release it, the initial velocity is 0, it just drops. Versus when you throw it, then you have some initial velocity. Josh? It's usually the convention for this particular textbook. Yeah. So if you're using feet and pounds for those types of problems, 32. All right. So now we have this information. We need to put in our initial conditions to solve for C1 and C2. We need the derivative. So this is going to be -2C1 e to the -2t minus 8C2 e to the -8t. And then we're going to put 0 in. Putting 0 in will give us 1. E to the 0 is 1. So we'll give us a couple of 1s here. So x of 0 is equal to C1 plus C2 is equal to +1. X prime of 0 is equal to -2C1 minus 8C2 is equal to 0. Now you have a system of linear equations to solve for C1 and C2. Anybody care to solve for that? Just multiply the first one by 2 or 8 or something like that and add it. For which one? You guys want to confirm that? Okay. I suppose we should graph this. Wait, let's get our final answer here. So next, first one is 4/3 e to the -2t, and then the next one is -1/3 e to the -8t. Just have to use x for this one. So overdamp means it doesn't pass through. It doesn't get to pass through the equilibrium. It just, when you release it, it just goes down and it goes down to zero, and then that's all that happens. And again, you have to look at this upside down. It's a little harder than looking at it sideways. Or I suppose we can just put a negative in front of it. But in any case, it's you pull it down, you let it go, and then it just goes back to equilibrium. So that's the idea of being overdamped. All right, the next part of the problem, I don't think it's much different. If we do this part B, we would just really be picking up from here, except mass is initially released from one point or at a point 1 meter below the equilibrium with an upward velocity. So here they just give us an upward velocity. Should we do it? No, it's the same. We get the same solution. X is equal to C1. So upward, I guess an upward velocity means what? So this is a negative 12 meters per second. So we can set up our system again. X of 0 is equal to C1 plus C2 is equal to 1. And X prime of 0 is going to be minus 2C1 minus 8C2 is equal to negative 12. So with an upward velocity, this might bring the spring back onto the other side, but it's still overdamped, so it'll still shrink down pretty quickly. Anybody interested in solving for this? If it's overdamped. Oh yeah, it shouldn't cross. If it crosses, it'll do something weird. C2 is what? What? 95? Positive. C1. Okay, let's check how this graph would look like. Oh, we should take a quick picture of this graph. And so with this one, we have, whoops, minus 2, this is a plus 5 over 3. That does cross because it gets pushed. Yeah, the up. Suppose we can. So if there's some force in the beginning, initial velocity, then that might move things up. Okay, so So now our last little bit is that you have this spring that's going up and down, and then you have a motor above it that's controlling, that's giving it some external force. So the two differential equations that we've been dealing with so far are homogeneous, and so the external force would be something, a machine, that would be kind of controlling this, and then that would give you a non-homogeneous system. So if we include the damping and the external force, we have now just a general system. So it's the same setup. And so let's just jump to the example. Wait, what's it say? Recall the solution is a sum of complementary solutions of a particular solution. Complementary solution is known as a transient term, and the particular solution is known as a steady state term. Okay, so let's see if we can come up with a, well, let's find an example. Sorry. What's what? Something with an external force. They call it, what do they call it? Driven. They call it a driven motion. It's going to try to squeeze it in the same page, but this will take a little bit longer because we have to solve for, maybe it won't take that long. All right, so it's the same setup again, except there's an external force. So let's see if we can do an example. And we're sticking with the metric system here. 2 kilograms attached to a spring. They give us a spring constant again. That's great. It comes to a rest equilibrium position starting at t is equal to 0. Force equal to this external force is applied to the system. Find the equation of motion. Oh, so this one doesn't have a damping force, does it? Oh yeah, find the equation in the absence of a damping force. So there's no damping force, but there is an external motion, so we can solve for it. So it looks like our equation should be simpler. Yeah, if it's simple enough, and I don't know if you would consider this simple, but if it's simple enough, then you can use the undetermined coefficients because it's one of these, one of the four, a combination of four functions that we know of. All right, so your differential equation is just going to be a mass is equal to 2, and your spring constant is equal to 32, and so I think that's going to be 2x double prime plus k, oops, let's say 32, x is equal to your function, your external force. So is that it? That's it, right? So this is your mass and your k. Your beta is equal to 0. And you have an external force. So to solve for this, we start off, well, let's see. It comes to rest. Because there's no damping. So damping, yeah, I didn't see that either until I read that. I was looking for a damping thing and then couldn't find it, and then I saw this. Um, I have any. Are there any initial conditions here? Find the equation of motion, absence of damping. Uh, comes to rest in equilibrium position. Starting at t is equal to 0. Forces. Yeah. So I guess we just have. Because the external force will take care of the movement of this thing. All right. So remember how to solve for a non-homogeneous. We first need to solve for the homogeneous portion. X double prime plus 16 if you divide is equal to, and then you have a new f function here, divided by 2. 68 divided by 2, 34. So the homogeneous part, x double prime plus 16x is equal to 0. So we solve for that. It's 4I, right? So your y or your x sub c, the solution, they use c or h, I think h. The solution for the homogeneous differential equation is going to be some constant times cosine 4t plus another constant times sine 4t. And then we can figure out the c sub 1 and c sub 2. Oh, that's going to be 0. Yeah, I know, but the homogeneous portion is just going to be 0. Well, I mean, the xp is probably going to be this just the solution for the force, but I'm just saying this part, the C1 and C2 will end up being zeros. So if we take the derivatives of this, this would be negative 4 C1 sine 4t plus 4 C2 cosine 4t. And then if you put 0 in for them, this is going to be C1, and that's equal to 0. And then you put 0, and that's going to be C2, and that's equal to 0. So C1 and C2 is equal to 0. This is not going to give any contributions at all because we're starting this from rest. And so everything is really going to function based on this F. So F, according to our equation, we should have x double prime plus 16x is equal to 34e to the negative 2t cosine 4t. And so we have to assume that our particular solution, we'll call it x sub p, is equal to linear combination of the sine and the cosine of these things. So a e to the minus 2t cosine 4t plus b e to the minus 2t sine 4t. And this is using undetermined coefficients. Okay. And Looks like we're out of time, so you can just try to solve for this. You can find the derivative, the second derivative, and then put it back into the function, solve for a and b. Okay? I think that's Green's theorem.